Thank you, Lucas. All right, let's get started. What's that?
I did not hear recording in progress.
I think it is. Yeah. If I click more, it says pause or stop. So yeah.
Okay.
Yep. I think we're good. All right, great. Well, it's an absolute pleasure to be here among friends to report on recent developments in the world of NERPI, in the world of black holes at home, and to announce the Black Holes at Home Apparent Horizon Algorithm, or BHaHAHA for short. Very quick motivation slide. Numerical relativity plays a really important role in this age of gravitational wave astronomy we find ourselves in particular when it comes to parameter estimation. That is the process by which we extract important science, the binary parameters, that is, from an observed signal. In order to conduct parameter estimation, it requires comparing the observed signal to millions of theoretical predictions. We're not proposing to do millions of numerical relativity simulations, but rather use catalogs of binary black hole numerical relativity simulations as the ground truth upon which we can build gravitational wave approximants. And when it comes to the next generation of gravitational wave detectors, it's well known, thanks in part to Deborah's pioneering work on this, that existing binary black hole simulation catalogs are simply going to be insufficient. We're going to need about an order of magnitude better accuracy and larger catalogs to cover the more diverse binary scenarios that we expect to see with 3G detectors. So accuracy and efficiency are absolute necessities moving forward. To this end, my approach has been in very nice alignment with Lucas's work, which is, we study systems that are not very box-like or cube-like. So why in the world do we keep using Cartesian grids to model these systems? That's the question I asked myself after many years of working with adaptive mesh refinement grids. Bottom line is they're suboptimal, right? They're not these fields aren't box-like, and these factor of 2 jumps in resolution transitions actually cause very problematic reflections. Something like 99.9+% of our numerical errors as measured by constraint violations are caused by interactions of outgoing waves with these refinement boundaries. So building on some pioneering work by Brown, Baumgart, Pedro Montero, et cetera, and in the context of covariant BSSN and performing numerical relativity in spherical coordinates with the same robustness as Cartesian coordinates, in spite of the fact that there is coordinate singularity on these grids. There are coordinate singularities on these grids. We built on this approach and extended it to cover spherical-like, cylindrical-like, Cartesian-like, even prolate spheroidal-like coordinates using our NERPI code generation framework, basically generalizing the reference metric approach to a much broader class of coordinate systems. And with that capability, the idea is to connect these multi-coordinate, multi-patch grids with smooth transitions, exploiting near symmetries. So you have high radio resolution in regions where you can get away with it, in regions where you can get away with low angular resolution. So numerical grid structures that look something like this. Notice that the R equals 0 does not appear anywhere on this grid structure. The reason being our time step is still constrained to the smallest grid spacing on the numerical grid. So we avoid R equals 0 and instead put, in this case, a very small pair of Cartesian AMR grids, surround that with spherical grids, and out here spherical grids as well. And with this capability, compared to a traditional carpet, non-llama grid structure, non-cube spheres grid structure, we can get away with something like 1/100th the number of grid points. That's 1/100th the memory overhead or less, and about a factor of 40 less in total CPU cost to perform a binary black hole simulation. It enabled me to, for example, perform a binary black hole simulation, the QC0 simulation on my cell phone some years back. Since then, Black Holes at Home has evolved, and we have, over the past couple of years, achieved some interesting science using Black Holes at Home. So last year when I came to this meeting, I reported that we used Black Holes at Home to test out new ideas in techniques that improve accuracy in moving puncture evolutions without increasing cost in any significant way. And to that end, I encourage you to take a look at this paper if you haven't seen it already. But you can reduce numerical errors in moving punctures in moving puncture simulations, binary black hole simulations, by orders of magnitude. And in terms of efficiency, Black Holes at Home has I've generated an entire catalog of binary black hole evolutions needing only desktop or laptop level resources. So with this comes in a very exciting possibility, that is bringing numerical relativity to the masses, bringing it to anyone who has a consumer grade level device. And yes, in past years, I would say, no, this is crazy, but I do think that cell phones can, in fact, if maintained plugged in, be used to further our efforts in preparing for the next generation of gravitational wave observatories. And with this, I like nothing more than to launch a volunteer computing project built around numerical relativity-based binary black hole gravitational waves generations. So a couple of years ago, I launched the first binary black hole simulation campaign. Largely, this was a stress testing exercise because a lot of these algorithms had never been tried before. So this helped greatly improve the robustness of them. As you can see, a great majority of these cases actually are processing cases. So our grid structure works just fine regardless of that. But as I said before, this catalog of simulations I performed helped me to develop new moving puncture methods that reduce numerical errors, not just in the context of Black Holes at Home, but also in the Einstein Toolkit. So the paper, in fact, just shows results using the Einstein Toolkit. So it is a universal, is it of universal benefit potentially for those who are using the moving puncture approach. But the bottom line is the campaign uncovered 3 issues, which since these simulations were performed, I've been working on. First and foremost, NeRPi, our beloved cogeneration tool, then known as NeRPi Plus, needed to be refactored. And there were a few reasons. Well, first off, let me just define what NeRPi is. NeRPi is a code infrastructure written in Python that enables you to quickly construct SymPy expressions in Einstein-like notation, and it generates for you highly optimized C code, leveraging for CPUs, single instruction, multiple data, SIMD, intrinsics, and common subexpression elimination to greatly reduce the number of flops needed to evaluate complex tensorial expressions like the BSSN right-hand sides, for example. NeRPi is I wrote NeRPi in order to do Black Holes at Home, to generate the Black Holes at Home code. So it incorporates all the necessary tools that you would need to leverage the reference metric formalism and generate Einstein's equations in any number of different types of coordinate systems. So NeRPi Plus, the NeRPi 1.0 version, I have to say this, it is the it was the first Python code I ever wrote. And it kind of shows. I'm a native, my native language is kind of like C. And so you see a lot of stuff where I didn't know about Python dictionaries or other very useful data types. And so, or data structures. And so that was there. And so some things were written a bit more clunkily than they otherwise could have been. That said, I'm very proud of the set of Jupyter notebooks that we developed, the NeRPi tutorial Jupyter notebooks, which provided and still does provide a very nice, I think, framework to teach the very basics from solving the wave equation. Everything is extremely well documented in these notebooks. I will say this summer I have a group of intrepid undergraduates who are working on porting these Jupyter notebooks from NeRPi 1.0 to NeRPi 2.0. So stay tuned for that. And here's the thing, I had big plans for BlackHoles at home. I want to get BlackHoles at home working on GPUs. I want it working on HPC for those extreme regions of parameter space, otherwise unattainable in a reasonable time frame running on a desktop computer. I want to add GRMHD, and these last two go hand in hand. In fact, all three of these go hand in hand. And thinking about doing this with NeRPi 1, yeah, okay. Now it's frozen up on me, lovely. Oh, here we go. Okay. I think I see what's wrong here. Oh, I know what's wrong. Just a second. I think I turned this way down. Yeah, because it was doing weird things. There we go. Now we should be able to hear it. All right, here we go. In the immortal words of Rocky III's Clubber Lang, this is what it would have been like. Okay. 18. Okay. 18's a slide, if it will play. There we go. Okay, so that's my prediction for continuing to swing NeRPi 1.0 behind me to achieve these. Okay, thank you, Clubber Lang. Okay, now we're getting a refuse to connect thing. Okay, here we go. All right, and this is a lesson I think we can all learn. And it's almost so true that I am hesitant to trust any code that doesn't have a 2.0 version or above.
Every single software project follows the same 2,000 lines. It doesn't matter whether you write it or you write it. It's all the same. If your project's only 2,000 lines of code, it's easy. But once it starts growing, once it gets past that, something kind of magical happens. And at 10,000 lines is where the maximum magic is. And what is that magic? Of course, it's the y-axis, which is regret. Decision you made to do these first 2,000 lines when life was good and coding was easy.
Okay. Truer words. Truer words. I challenge you to find them. I challenge you to find them. So, in my regret of the first 10,000 lines of NeRPi 1.0 code, I wrote NeRPi 2.0. I spent the time, this has been a few summers ago, in preparation for extending NeRPi to achieve all the things it can and should achieve, HPC, GPU, and GRMHD. So basically, NeRPi 2.0 is basically an entirely refactored version of NeRPi 1.0. It's pip installable, a feature request I had for years since NeRPi 1. So, and here it is right here. And quick start step 1, very proud of that. Pip install NeRPi and it's on your computer. And on this foundation, we have released a cluster of papers over the past 6 months or so. First, Groovy, where we've added using, as Leo described, Grail, our Grail library, which is basically numerical recipes for GRMHD. This was implemented in only a couple of months. Samuel Tootle meanwhile worked on our GPU capabilities. So we now have GPU capable NERPy black holes at home, at least for single grid evolutions with full numerical relativity. And that is working beautifully. And in terms of benchmarks, a typical consumer grade NVIDIA, gamer-like card versus a high-end consumer grade CPU, it gets us about a factor of 5 improvement in performance. I'm not going to give you the crazy, sorry if it's a Vinci one, comparing to one CPU core because that's not fair. But yes, so comparing a full CPU to a full GPU, that's the number we care about, and we get about a factor of 5 improvement in performance, which is huge. That's 5 times more in spiral orbits. I'll take that, sorry. I will take that. And finally, last but not least, this is the most recent one, Superb NERPy. So Superb is a supercomputer-ready version of black holes at home, which is a CUDA, a Charm++ parallelized version of black holes at home, again, for single grids. So think spherical BSSN, but it can also do spherical-like, cylindrical-like, Cartesian-like coordinates, all on a very, in fact, the strong scalability is very impressive with this code as well. So, and I'll say that it's written in such a way that if you're already working in the black holes at home infrastructure, it's pretty quick to get up and running. So Terrence, my graduate student, actually took Groovy and put it into Superb. It took all of 2 weeks, and he was up and running on HPC. He's currently doing bar mode unstable neutron star studies. So bottom line, the first issue was resolved, and it has led to a nice little flurry of papers, hoping to build on those. The second issue, this is one of the more annoying ones. So if we look at the constraint violation, this is with these moving puncture improvements enabled, by the way. If we look in the strong field region, we see that the Hamiltonian constraint, like an L2 norm, excluding the volume around the horizons, you can see that it's in pretty good shape, actually. It's pretty nice. And this is over thousands of M, multiple orbits. In the wave zone, also constraint violations looking very nice. There's still a very small, well, there's a bit of a bump here just due to that not so sharp gauge feature propagating out. Without the improvements, this would be orders of magnitude higher. So you can see it's looking nice. But then when we look near the outer boundary, outside the realm of physical interest, I might add, we see instabilities happening in a handful of cases. Trouble at the outer boundary. So what the cause of this, I found, after about a month of debugging, was the problem has to do with the fact that when the black holes move, the entire grid structure, space-time fields on every grid point are interpolated to the new grid. And sometimes interpolations amplify the noise exponentially on the z-axis only near the outer boundary. And I found this instability. I could turn off the instability basically like a light switch if I just set the regridding frequency just right to minimize the amount of interpolation happening along this z-axis. The solution, and this is real, these are real grid points. These are actual data I generated this morning using the latest multi-patch algorithm in black holes at home. What you'll notice is, first, look how beautiful this grid is. I have to say, I mean, I'm slightly biased, but look at the resolution difference between the patches. A typical gap in resolution in black holes at home between patches is something like 1.4, whereas Cartesian AMR, we all know it's 2, and that's a flat number. And in fact, I'm working on, I'll talk about this near the end of my talk, working on dropping that even further. The goal being, of course, minimize resolution transitions between grids as much as possible, because we know those are troublesome. Yeah? Plain BSSN, except with my improvements to the moving puncture approach, which are universally helpful. So, oh, sorry. Yes, the question is, am I using any kind of special technique to damp out the constraints after each, say, regridding or what have you? And the answer is no. I'm not. Yeah. I'm sure it would help a little bit. Oh, you mean with the error that causes the crash? That, I think, is, and actually, you have to throw in the fact as well, it's not just interpolation, we're also applying outer boundary conditions there. And so, and also things are moving super duper luminally. That's a technical term. It's way, the grid points are moving 20C, something like that. So a tiny bit of information from interpolation error, from outer boundary application error, on occasion becomes superluminal, that information, and that's just a dead giveaway. That's a CFL violation, basically. It's possible I could also tamp down, by the way, these exponential growths by just decreasing my time step. But who wants to do that? But it would require a big drop. Problematic. Anyway, so anyway, now that we've admired this sufficiently, by the way, these grids in here, this purple and blue grid, these are actually, if we zoom in, sorry, I can't zoom in, but these are actually Cartesian grids. They're rounded Cartesian grids. So when you talk about this multi-patch approach, you have an option. Say if you have a Cartesian grid inside a spherical grid, for that interpatch boundary to be either cubical or spherical. In this case, I chose spherical. It actually works a little bit better, just empirically speaking. So here's my solution to the problem. As you can see, we now have full capabilities to have the inner grid go on a sliding boundary here. So this outer grid here does not rotate at all. And that is my solution to the problem, bottom line. We never had any problems, again, in strong field, even in the wave zone. It was the outer boundary, the fact that we were interpolating data that super duper luminally. So the bottom line is, I believe this is fixed. Next, not a popular thing to say, but it was an issue that we depended on the Einstein toolkit. I'm sad to say, because the Einstein toolkit, well, two facts. First of all, it was clunky, and let me just go over this. The reason why we had a dependency was because we needed a good apparent horizon finder. Like many numerical relativity codes, these apparent horizon finders, of course, provide a couple of very important functionalities to this code. One being diagnostics, black hole diagnostics. We need to be able to tell people what and confirm, in fact, what are the black hole spins during in-spiral, what are their masses during in-spiral, and finally, what is the final mass and spin of the remnant black hole. Super important diagnostic, just physical diagnostics. Another thing, another aspect to this is the fact that, well, black holes at home enables you with this grid structure to adapt your coordinate system live during the actual simulation. So when you're doing a high spinning puncture evolution and that black hole goes from a near sphere to something more like a pancake, you can resolve, you can add grid points in one direction appropriately. That's the goal, that's the idea. So we really do need a apparent horizon finder. So my idea was, and in fact, in the first set of the first BBH catalog from Black Holes at Home, we actually use the state-of-the-art AHFinderDirect Einstein Toolkit form. The problem being, of course, it's not portable. I don't know if any of you have tried, but it's a bit of a mess. It's a bit, it has its tentacles deep into the Einstein Toolkit infrastructure, and it's very difficult to extract. I've tried a couple of weekends, wasted weekends, but not entirely wasted, I guess, because I learned that I'm going to just have to write my own if I'm going to get something that does not work. So I did collaborate with other maintainers of the toolkit. Roland, not naming names, but Roland helped me. And the solution ended up being this. We weren't quite successful to just convert the Einstein toolkit into a library where we could just call a function from the toolkit. That would have been lovely, but it didn't quite work. It would never release memory was one problem. So the solution we found that worked, at least, was 2 executables. I'm not sure, Hungray, if you use this approach as well. Do you run the Einstein toolkit separately as an executable during your code's execution? Post-processing. Okay, yeah, okay, that makes sense as well. Sorry. Oh, I asked the question though. Oh yes, he said he uses he does all of his apparent horizon finding post-processing. Yes, thank you. I mean, the thing is, this is an ugly approach, but it's functional. But think about this in terms of the volunteer computing project. 70% market share operating system in the consumer market is Windows. And it only took a quick conversation with Roland to realize this is not going to happen anytime soon, unfortunately, getting Einstein Toolkit to just compile on Windows, other than the fact that this is an ugly approach. So I decided to write BhaHaHA. So BhaHaHA abides by my group's core philosophy. That is, whenever possible, we want to provide code to the community in a way that does not care about the infrastructure being used. So NERPy is one case in point. It can generate, of course, BlackHoles at home, but it can also generate Einstein Toolkit thorns. It can also generate CarpetX thorns. You just pip install it, and it kind of works. And it has all these nice features. Another feature that was recently added over the past year is it actually can now, this is really cute because BlackHoles at home, the goal is to generate huge gravitational wave catalogs for gravitational wave approximates. What is this but a new gravitational wave approximate? So the idea is use BlackHoles at home, use to improve this, and you can use this while running BlackHoles at home to predict how long it's going to take for your simulation to complete. How cute is that, right? And even check your waveform against what the prediction is from SEOB and RV5 plus Bob, the backward one-body model. Grail is another case in point. Leo talked about this in his very nice talk yesterday. It's an infrastructure-agnostic GRMHD library. It is the numerical recipes of GRMHD, if you like. It's based on and validated against the trusted Illinois GRMHD code. It extends the original Illinois GRMHD code with finite temperature macrophysical EOS. It has neutrino leakage built in. David Boyer, who is here, Leo, who is here, both of them are in my group, as well as Johnny, have been collaborating to incorporate M1 support into this, and the Einstein Toolkit implementation of the M1 algorithm is underway. As I said, Terence Pierre Jacques actually used Grail to add GRHD support it's only like 2 months, okay, 8 weeks. Not bad, I'll take it. And then BhaHaHA. BhaHaHA is the latest code in this series that abide by our core philosophy of being infrastructure agnostic whenever possible. So BhaHaHA is a library. It's an AHFinder library. It has already been implemented successfully in 3 different, in our infrastructures, Einstein Toolkit, BlackHoles at home, and I'm proud to report DendroGR as well. So yeah, as I said, BlackHoles at home, superb. They need a live horizon finder. And the problem is, AHFinderDirect presents a very challenging point of comparison because it's fast. The darn thing is 20 years old and faster than anything. It is crazy fast, so good. How do we even come close? Well, I'll talk about that. Okay, so what does BhaHaHA do? Well, just like any apparent horizon finder for 3-dimensional space-time slices, it tries to find the MOTS, the outermost, marginally outer trapped surface. And the outermost MOTS is defined as the apparent horizon. BhaHaHA is unique. In the past, when we talk about flow algorithms for finding apparent horizons, you often hear terms like fast flow and stuff like that. Basically, what it does is it converts the MOTS equation, which is an elliptic PDE in 3 dimensions, into a parabolic equation, where in pseudo-time, you basically relax using this parabolic approach, PDE, basically, an iterative approach. BhaHaHA, on the other hand, is the first ever hyperbolic flow method. So it hyperbolizes the elliptic PDE in a very trivial way. You just take the MOTS PDE elliptic equation and you plug it into a damped wave equation. You don't have to linearize anything. You don't even need a good initial guess. It has all the robustness of a flow algorithm, meaning you can choose any sort of terrible initial guess you'd like, as long as it's larger than the horizon. It will find that horizon. And do so leveraging, by the way, it uses spherical coordinates. Before the big breakthrough of numerical relativity and spherical coordinates, people generally shied away from using spherical coordinates in their apparent horizon finders. We don't shy away from it because that problem has largely been resolved by use of reference metric approaches. The challenge I presented to myself, I posed to myself, was can I make BhaHaHA as fast as AHFinderDirect? Let me say, first off, I'll accept within a factor of a few, okay? AHFinderDirect is pretty darn fast. Well, with its default, so first off, just setting the stage here, I'm trying to find a quote unquote difficult apparent horizon. It's basically the point at which this 4-to-1 mass ratio Brill-Lindquist data, the slice, has just formed a common horizon. So it's a rather egg-shaped looking creature. In BhaHaHA, with its default resolution, takes about 14.5 seconds to find this horizon. AHFinderDirect, 1.4 seconds. It's not bad. Good job. But bad on us for not being fast enough. So about a factor of 10 too slow. What do we do? Brainstorm. How about we try something like a multigrid-inspired approach? Now, a traditional multigrid approach would require that we linearize the elliptic PDE and basically relax on the residual. You can do V's and W's if you've heard of these things. That principle can work, and it actually has been. Like the first apparent horizon finder paper in probably 15 years occurred just last year, in which a group presented an actual multigrid approach. But the process by which they linearize the PDE, it's a pain. In my book, I don't want to touch the equations. I just want to solve them. Okay, so here's our approach. We relax at a low resolution with a poor initial guess. We use that relaxed solution as the initial guess for the next higher resolution, double the resolution. Then we use the relaxed solution to that, interpolate the solution to the highest resolution, this prolongation approach, basically. And then we relax at that resolution, and we're done. It does not help at all because we're not looking at residuals here. We haven't linearized this PDE or anything. It doesn't help to go do V cycles or W cycles, what have you. This alone, though, improves its performance by more than an order of magnitude. But I'm not a patient man. We're 4% slower than AHFinderDirect on this horizon. I'm sorry, that is unacceptable. Yeah. Oh, whoops. I am faster. Okay. Yeah, I was looking at the wrong number. Sorry. Okay, I'm 4% faster, but that's not fast enough. Okay. So the next idea, over-relaxation. Sorry, I just updated these numbers with the latest BhaHaHA. Okay, over-relaxation. So we all know it and love it, right? This is used often actually when solving elliptic PDEs. It's a numerical linear algebra technique to quickly get a solution. So basically, the idea is you linearly extrapolate a previous and current solution to a later iteration, and you increase the later iteration until what we measure the maximum residual on our BhaHaHA grid is minimized. And with this, we're about, this number is correct, 20% faster for this particular scenario. Now, before I go further, I need to make things very, very clear. BhaHaHa has another optimization that simply was not available 20 plus years ago with AHFinderDirect, and that is OpenMP. Oh, and by the way, the irreducible mass agreement, pretty decent, pretty decent. And I'll quantify this a little bit better in a couple slides. So what happens if we do it completely apples to apples, if you will, and only look at one core? Well, it shows right here, we're within a factor of 2. All these timings are in seconds. It's trying to find, again, this common horizon, which is the toughest horizon here. It's a factor of 2 slower at one core, but it seems to be optimal right around 8 cores, where, as I showed before, it's about 20% faster. So implementation note, if you're interested in making it run as fast as possible, somewhere around 8, 12, 10 cores is pretty close to optimal there. And notice that a significant fraction of the runtime is being spent in the Einstein Toolkit, actually, just interpolating the data from the numerical relativity grid onto the grids needed by BhaHaHa. That's also true with AHFinderDirect. It has to interpolate data from the Cartesian AMR grids to its own grids. So the bottom line is, even without OpenMP, we're still within a factor of 2 performance of AHFinderDirect, and I will take that. Still, it's a very small fraction of your runtime if you have a sane frequency of finding. Yes, please.
Okay.
Oh, hey, Eric.
Hey, good to see you and good to listen to you. Quite interesting.
Oh, sorry. Let me turn up the microphone in a second. Sorry. I mean the speaker.
I hope you all can hear me. I want to make a comment regarding the fast flow method, because you mentioned it's parabolic, and that's not quite correct. The fast flow method relies on a spectral representation, and then each spectral mode takes a different time step size. So in the end, it has the same speed as a hyperbolic method, because the high frequencies take a small time step size, but that's what you want for them. And the coarse frequencies take a large time step size. It's like the grid decomposition that a viewer shown, except it does it all the time because it's based on a spectral method. Anyway, just a correction, because I like Gundlach's work very much.
Yeah, I'm really just quoting Thornburg in stating in kind of placing it in that category. But yeah, it is different time steps depending on which mode. Yeah, fair. That's fair. Perfectly fair. Thank you. Another aspect I really was curious about was what happens. Let's just say, right, code units should be invariant when we're talking about vacuum spacetimes, right? It should not matter what the total mass is of our system. We should be able to rescale it to whatever value we want. So here I tried 16 decades in mass scale, and BhaHaHa is, all of its parameters are set in a mass invariant way. So if a parameter has a mass scale, it factors that out, and you specify it in your inputs. And no matter what I did, I could not get AHFinderDirect to find the common inner horizons for this scenario when the total mass of this system was set to 10 to the minus 8. Remarkably, it found it around 10 to the minus 5, except for the second inner horizon, which is a smaller black hole here. And it found it through the 3 decades we normally would care about, I would say in quotes. But again, this should not matter. Your total mass should never matter in a numerical relativity simulation. And then 10 to the 5, 10 to the 8, very strange. It's like it converges, AHFinderDirect is converging at levels like close to its initial guess. It's like a false convergence almost, very strange. Whereas BhaHaHa, you see the results are completely invariant to any of these mass scales. More practical scenario, the GW 1509-14 Galler example from the Einstein Toolkit. So this is using the Einstein Toolkit implementation of BhaHaHa. And here I'm just showing you the in-spiral trajectory of the smaller black hole. And here is delta R over M over time. As you can see, we're at down to 10 to the minus 5, 10 to the minus 6 level. So we have really good agreement here in horizon centroids. One other speed up that I implement in BhaHaHa in the case of an inspiraling black hole, just simple up to quadratic extrapolation from past horizons, both for the surface as well as the centroids. So it gives it a better initial guess, as good of initial guess as it possibly can. But here's a really interesting question. And I don't know if this has been fully explored in the literature. But what tolerance is reasonable? Right? AHFinderDirect, if you look at its defaults, it sets the L infinity norm of the residual to 10 to the minus 8. But check this out. If I just change the interpolation from the AMR grid from third order Ermey, which by the way is the recommended interpolation algorithm for AHFinderDirect and also BhaHaHa, if I just change it to fourth order Lagrange, same tolerance, you'll notice that there is a systematic offset. So orange and blue here are overlapping very closely. That's good. That's actually AHFinderDirect versus BhaHaHa, same interpolation. But you'll notice there's a bit of an offset when we look at fourth order Lagrange. And then if we just look at the relative error versus time, here's the average, this dashed line. Control versus fourth order Lagrange, both AHFinderDirect, we get the average error being about 1 part in 10 to the 5, which is keep that in mind. And then if we look at the control, which is third order error meet AHFinderDirect versus third order error meet going into BhaHaHa, so same metric data going into AHFinderDirect versus BhaHaHa, and BhaHaHa tolerance set to 10 to the minus 5, we get this. So it's actually agreeing better. Now, if you look at the abstract of the AHFinderDirect paper, I found this very interesting, finds an apparent horizon to about 10 to the minus 5 accuracy. It tracks. So happy to see that. And it also says that having the default accuracy at 10 to the minus 8 is overkill. You could get away with a lot less than that. So here we have, using the same tolerances for AHFinderDirect and BhaHaHa, 10 to the minus 5, now that we've calibrated it, we see that BhaHaHa, this also uses OpenMP as well, is about a factor of 2 faster. And that's also aided by the fact that, again, we're using this up to quadratic extrapolation to predict the next horizon. Use that as our initial guess for the next find throughout the in-spiral. So it's the over-relaxation, the multigrid-inspired, plus this extrapolation. And yeah, that's basically the same plot I've already shown. Now, what about precision horizon finds? All the horizon finds I've shown you to this point, we're only looking at tolerances of about 1 part in 10 to the 5, which is kind of the default. And actually, quite frankly, constrained by the interpolation error from the numerical relativity grid. Important fact. What if we didn't have that restriction? In other words, what if instead of using the Einstein Toolkit implementation of BhaHaHa, we used the BlackHoles at home implementation, which allows for curvilinear grids like spherical coordinates, like what I used here. So using spherical coordinates and interpolating onto the spherical coordinate grids of BhaHaHa to try and minimize errors, and using very high resolution grids, by the way, I was able to find that. So this is a really cool question. Okay, you have 3 Brill-Lindquist black holes. Say they're in the XZ plane. They're all equidistant from the origin, which is right at the center. Sorry, let me use my mouse. Right at the center, right here. What is the maximum distance from the origin such that a common apparent horizon still exists? It's a very well-posed problem, and therefore something I'd love to just try out. So AHFinderDirect, through hook and by crook with, I can't imagine, 20 years ago, equipment, managed to get 1, 2, 3, 4, 5, 6, 7, and then an error bar on the 8th significant digit. Using much higher performance machines, I'm in agreement with BhaHaHA is in agreement with AHFinderDirect on this last digit within the error bar, and I was able to bracket it to an extra digit or so. So happy to see that we receive, and this is starting from a very crude bracket and just zeroing in using the traditional bisection approach. It was more than bisection because it had multiple nodes running on this, but yeah. Okay. So before I continue, any questions about BhaHaHA or yeah? Yeah. So the question is, does BhaHaHA assume the surface to be star-shaped or Stroop-Koffer? And the answer is yes. It uses the same basic assumptions as other mainstream AHFinders do. Great question. Thank you.
Well, there's a question online, but
Yeah.
go ahead on. Yeah, I think.
Okay, online. Sure. Yeah, Jonah.
Yes.
Yep. Hi, Zach. Nice talk so far. Thanks. So I know that you're also thinking about GPUs. So
Yep.
how do you envision apparent horizon finding working when your data is GPU resident?
Yeah. So as I showed in an earlier plot, a good chunk of the time, in fact, a majority of the time, is often spent just in interpolating the data from your 3D grids. My thought is the most efficient way of implementing BhaHaHA would be let the GPU do the interpolation and then send the information to a CPU that has multiple cores and just use that and run BhaHaHA asynchronously. Yeah, that's my thought in terms of like a task-based parallelism framework. BhaHaHA in principle could be run on GPU. It would take a bit of effort. I mean, just in terms of number of lines of code, so AHFinderDirect is something like 30,000 lines. BhaHaHA is about 1/10 that. So, you know, it's still under the 10,000 line where things go crazy limit, but you know, it would take a bit of effort, no question.
Yep, that makes sense. Thanks.
Yeah. Yeah.
Okay, so this Brill-Lindquist BlackHoles test, was that something Jonathan did in his original paper?
Yes. And the most recent apparent horizon finder paper, which just came out last year, also Lynn and Novak actually. No, it's not analytically. It's using numerical, using numerical data. It's not doing anything analytically in this case. Yeah. So it's using, so Gret's a great question. So the question was, is this using any like analytic data, feeding it directly into BhaHaHA? The answer is no, but it is just initial data put onto a numerical grid, and it's a Brill-Lindquist initial data. Being the case, there's really only one metric quantity, and that's a conformal factor at the end of the day that it actually has to work on interpolating. It's a scalar too. So this is a relatively easy test. Yes. It still has to do a lot of calculation on top of that and interpolations, frankly.
I have one more question. Robust, you said that will converge to the apparent horizon stuff on the outside. It doesn't grow if you start inside?
Yeah, this is a known feature of or characteristic of flow methods. They're only guaranteed robust if your initial guess is bigger. However, in practicality, the horizon does grow in these in binaries, in spirals. Like especially early on, you can see the area growing very rapidly. It's very rapidly. It's silly. But the coordinate size does grow very rapidly early in the evolution of a moving puncture. And as a result, very early version incarnation of BhaHaHA may have had some issues. But with this extrapolations enabled and stuff, it's very, very robust now to the rapidly growing phases and whatnot. So yeah. And by the way, if it does fail, the Einstein Toolkit implementation at least will reset the initial guess to the biggest spherical volume that you gave it initially. And I've not seen it fail after that. So yeah. Great. Any other questions on this before we continue to the last bit? All right. So the last bit is looking ahead at the next binary black hole simulation campaign. This is really the dress rehearsal for volunteer computing project launch. So what remains? Not a huge amount. I need to move over the interpatch basis transforms from NeRPE 1. Naturally, we're not just evolving scalar quantities in BSSN. It works, by the way, for that grid structure where you saw the sliding boundary. That works just fine if you're evolving a wave equation, actually. It will evolve just fine with the grids patches, by the way, with the grids sliding and rotating inside there. I validated that and even found nice convergence. So what remains is I need to port over the basis transforms. A waypoint along the way. I really, really want the waveforms generated to be from initial data that are conformally curved. For one reason is for consistency, because at some point we want to do these evolutions with high spins above what conformally flat initial data would allow, which is going to be like 0.85-ish. I want to go way above that. I also want to do scattering experiments with this. So high Lorentz boosts, higher than the limits, again, imposed by conformally flat. And that's the bottom line. So I'm working this summer on getting NeRPE elliptic set up on the multi-patch grid structure. It will also, by the way, enable for the first time, I think, well, maybe not the first time, because Spectre has their initial data code open source, but high mass ratio. With two punctures, for example, two punctures solves the elliptic PDE for conformally flat binary black hole initial data on a single patch. It's a single grid that has two foci. It's called it's akin to perlate spheroidal coordinates, basically. And perlate spheroidal coordinates do not allow you to add more resolution around one of the foci as compared to the other. As a result, talk to some folks who have done high mass ratio in spirals using two punctures. It can take weeks to generate one initial data set with a very high mass ratio, just because you have to have the highest resolution around both punctures. And that's problematic. So I want to get around that first by taking the current NeRPE elliptic, which only requires solving a scalar PDE. And I've already demonstrated that with the latest black holes at home grids, we can solve that kind of equation without any trouble, and then move on to the conformally curved initial data, which Tiago, my former student and now collaborator, has already successfully implemented for single patch black holes at home. So I'm going to be working on that this summer. I'm also going to be working on outputting data, getting it ready for Spectre CCE, building on Hongre's work and Deborah's work. Where'd Deborah go? Anyway, Deborah's work. And try and get that implemented. And finally, this is something I'm pretty excited about, because this has to do with, there's been a lot of work in addition in getting a new multi-patch algorithm up and running. And that new multi-patch algorithm, you've already seen, it allows for sliding boundaries between the strong field and the weak field region. But it also allows for a lot more diversity in the grid structure. And that's super exciting. If you look at the minimum time step, the minimum grid spacing, which sets the overall time step for these simulations, it's actually not here at the center of the black holes. It's actually here, where the spherical grid, this is a z-axis right here, where the spherical grid, you're looking at the North Pole, if you will, of the spherical grid here, the South Pole here, North Pole here, South Pole here. The time step is, the grid spacing is smallest here, 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 and here, which is very annoying. It's only until you get to about 6-to-1 mass ratio, maybe 4-to-1 mass ratio, where you actually see that the minimum grid spacing is inside the black hole box, which is completely silly. So I have a solution, and it's this. It's called the wedge ring grid structure, which completely removes coordinate singularities from the grid structure. I'm showing here just the grid points that, the closest grid points to these boundaries. I'm not bothering to show the the overlaps or anything like that. But this gives you a pretty clear idea. So you have a Cartesian-like coordinate system here. It's rounded, and that's how it looks, kind of like a Minecraft sphere. And then the grid here, this is one grid to the left and right. So what this is simply spherical coordinates where you take the region from theta equals 0 to pi over 4 and the region from 3 pi over 4 to pi, and you remove it. So we have now a ring, an axisymmetric, beautiful ring grid. But we have two holes. We have a hole at the top, we have a hole at the bottom, where we've just taken out the z-axis. Basically, we've excised the z-axis. What do we do? What do we stick there? And the answer is very simple. Make a copy of that ring that we just created, and we're going to get out our sword and chop right down the middle, 90 degrees, chop it again. What we end up with, we'll pick up two of these pieces, okay? It's a rounded pyramid with a chunk taken out of the top just because we have a Cartesian, we want to put the Cartesian grid there, okay? Does that make sense? Now you take this is our wedge. So the ring that I described earlier, that's naturally the ring. That's this grid. This is one grid to the left and right. And the wedge, you stick one wedge up here, stick one wedge down here, and there you go. Volume filling also has some nice properties. The radii are perfectly collinear. There's no, basically what this means is if you want to communicate information from this grid to this grid, it's two-dimensional interpolation. You don't need three-dimensional interpolation at all. It's lovely in that sense. It removes the z-axis. I'm a huge proponent, naturally, of a staggered vector potential algorithm for evolving magnetic fields. We cannot use a staggered a vector potential formulation on a grid that has coordinate singularities, because it would require that we sample at the coordinate singularities. One of the key features, or one of the key, I guess, constraints of the numerical relativity and spherical coordinates approach is you have to sample away from the coordinate singularities. If you sample at the coordinate singularity, analytically it would work if you could take proper limits, but it's like a 0 divided by 0 numerical problem. And so we avoid it. And as a result, when we take derivatives across these, we're only taking derivatives of smooth quantities. Everything behaves very nicely. However, you cannot sample. So what this will enable, if you can imagine, let's say we just had one of these grids like we have here. Let's stick a black hole down here and an accretion disk. This grid is perfect for black hole accretion disks. Because look, you don't have an accretion disk on any z-axis. The grid is perfectly regular up here. You also have, for the flow of the accretion disk around the black hole, it's moving along coordinate lines, minimizing spurious angular momentum loss as a result of, on a Cartesian grid, like imagine if you had a Cartesian grid, right? If it's going, here's the x-axis, let's say. If it's going along the x-axis, everything's great. But as you rotate, what you'll notice is the effective resolution of that fluid element drops by √2 delta x. So it drops by √2. And then it goes, so it's being resolved well, slightly under-resolved, resolved well, slightly under-resolved. And the problem is so much worse, though, if you have AMR grids, right? Because suppose it crosses an AMR grid box. Then here, let's see, it could be, yes, right. So here it could be very low resolution, then it crosses the corner here, and now it's doubly resolved, very high resolution, then it's lower resolved. Imagine trying to model MHD turbulence on a grid like that. Not recommended, not recommended. It's not a very good grid structure for that. But this is perfect. And I should admit, this grid structure is not something that I learned that I came up with it, but then I learned that someone else had come up with it already. Mark Avara, author of Patchwork MHD. And he called this what I just described it as, the perfect black hole accretion disk grid. So pretty exciting. And so the idea would be for black holes at home, we simply replace those small spherical grids below and above by this. Notice that it meshes so nicely with the Cartesian grid structure here. Whereas before we had a tremendous density of grid points along the z-axes, the z-axes of these two spheres right here. So the grid space would be very tiny here, but very coarse here. It's not good. Even though the average grid spacing was, the difference in grid spacing between patches was about 1.4 to 1. With this, it could be much closer to 1 to 1. So I'm very excited about moving on to that. So I encourage everyone to stay tuned. We have a lot of fun things coming down the pipeline. Thank you.
Any questions in the room? Yeah, a quick question. Some really great stuff here with BhaHaHA, and we've already used AHFinder for lots of interesting stuff, and you're right, AHFinder is really fast. But I wanted to ask, have you guys tested BhaHaHA for hypermassive remnant from BNS merger when it does the final collapse to a black hole? Because we've tested that with AHFinder, and AHFinder does a fantastically good job on the last very instant when the collapse happens. It's fantastic results. But there's a really key thing that AHFinder does, which most people don't see or pay that close. So there's a constraint on rotating black holes about when a hypermassive remnant can collapse a black hole, and that is the total angular momentum has to drop down enough in order for it to collapse to a curved black hole. And AHFinder gets that almost perfect. It does amazingly good results, and the final collapse happens very fast, but it won't go until the total angular momentum on the hypermassive remnant has slowed down enough. So I was curious, have you guys gotten to the point where you've tested that yet with BhaHaHA, or that's still, you haven't gotten to that yet?
Yeah, it's definitely. Yeah, so the question is, have we tested out BhaHaHA in the context of a collapsing neutron star, or perhaps from a binary neutron star merger remnant? And the answer is we haven't yet. But I'll say this: we have something that AHFinderDirect does not, and that is I've implemented a BBH mode. So for binary black holes, at least, we have, you have two independent horizons. They in-spiral. With AHFinderDirect, basically what you do is you tell it what iteration you expect the common horizon to form around. And then it will start looking for it after that time. What BhaHaHA, yes. I've always been annoyed at that because I'm not a great guesser. And so in BhaHaHA, what it does is it actually communicates the information between the different MPI ranks. So BhaHaHA is parallelized the same way AHFinderDirect is, one MPI rank per horizon. So up to 3 MPI ranks are being engaged in the horizon find for a binary black hole merger, in-spiraling merger. So what it does is it communicates the information about the radii, the maximum radius of each individual horizon, as well as their positions to all ranks. And in doing so, we're able to turn on the common horizon find when and only when it is reasonable geometrically. And once it is reasonable geometrically, it starts to search. It finds it. As soon as it finds the common horizon, it disables the individual horizon finds, which is another feature. Yeah.
If we could try it on that case of a hypermassive remnant doing the collapse to a black hole, we would love to try that.
Yep.
But what you're describing so far is lots of cool stuff that we can't do in AHFinder. We'd really love to try your code on this particular case.
It's ready. It exists. Yeah. Well, really, it's just a matter of sending it the information. One very key thing that you would look for when it comes to collapse and when you should start looking for a horizon is look at your maximum density on your grid. Generally, when the neutron star collapses, if you're doing a moving puncture evolution, you'll see the maximum density over your entire grid structure jump up. You can turn a trigger on, actually, in the Einstein toolkit. When the density reaches a certain threshold, then and only then, or the lapse collapses. That's another way of looking at it, of course, the lapse collapsing. When the lapse drops below a certain threshold, then and only then you can turn on BhaHaHa.
Sorry to cut this off.
Oh, we're over time. Yep, sorry.
Eric maybe has that. If it is a quick comment, we can take it. Otherwise, I'm gonna have to ask him to postpone it.
Okay, a quick comment. I want to point to a paper by Oleg Korobkin. The URL is in the chat. He studied GR accretion disks in a multi-patch system, and he has a distorted multi-patch system, even more adapted to the accretion disk. And the other thing is a paper that we wrote more than 20 years ago about pre-tracking. This is finding surfaces before an horizon has formed to find out where the horizon will form. The URL is also in the chat.
Yeah. Thank you, Eric. That's very helpful. Thank you.
All right, so let's thank Zach once again. I let our clock extend like 10 minutes or so because we started a little bit late, but in the interest of keeping time, let's resume 3:30, or let's resume our talks at 3:30 with Sphinx DSSN by here.